giving you a summary of the included publications and projects. But before I go into all my papers, I would like to take you on a very short and brief historic excursion to see how humans tried to describe volcanoes and their underlying plumbing system in the old days. So if we look back, early descriptions that can be found in the literature are usually more in mythological terms than in scientific terms. For example, we have the legend of Pele on Hawaii, who's the goddess of fire and all lava. The Romans had Vulcan, who is in his forge beneath the island of Volcano. And the Greeks, they had a legend about a Titan who lost the battle with Zeus and was buried under Etna, and who is responsible for all that Etna does. If we go a bit further, maybe the first concept that is resembling a magma plumbing system can be found in a book called Mundus Subterranean by Athanäus Kirchner. Kirchner was a polymath and German Catholic priest who did his studies in Rome. So what we can find in this book is the following diagram. It's very intricate. We can see that Kirchner imagined a network of underground fires which are connected to the surface to volcanoes and erupt through them. However, Kirchner also believed that water formed a similar network, and the two sweetly conspired in mutual service. Fast forward a couple of hundred years, most scientific concepts were introduced, and by the 20th century, most fundamental concepts of igneous magmatic systems were there. Magmatic plumbing systems were initially viewed as single melt-dominated chambers, which were located quite shallow under volcanoes. In the last 2 decades, a new concept seems to be emerging, one which is of trans-crustal magmatic systems. So we have several chambers and storage levels throughout the crust, down to the mantle, and we have different domains of magma, mush, and the surrounding host rock. So this is where I come in and where my thesis lies. So the aim of my thesis is to investigate magma plumbing systems in several contrasting volcano-tectonic settings in order to improve our understanding of the architecture and dynamics, and eventually to contribute to the current paradigm shift from a single magma chamber to a trans-crustal approach. Here's a short overview of the papers that we produced in the last 4 years. And in the next few minutes, I would like to take you on a short world trip. We'll be starting with the different study areas. We'll start in Iceland in the north. Then we'll go to Gran Canaria and the Canary Islands, over Cameroon, to our final destination, which will be Bali in Indonesia. So let's start in the north and let's go to Iceland. When I started my PhD in 2014, it so happened that there was an active eruption going on in Iceland. And I was lucky enough that some colleagues from the geophysics department went on the field trip and brought back some samples. And I got my hands on these fresh rocks. So let's see, what did actually happen in 2014? There will be some names that are going to be reoccurring now. I'd like to introduce them first. So you have a map of Iceland up here again, and we are located right in the center. We have Bardarbunga Central Volcano, which is located under the Vatnajökull ice sheet, or glacier, within the Bardarbunga fissure swarm, and which is part of the Bardarbunga-Vetigötten volcanic system. At the same time, we have Askja Central Volcano, located further north, in the Askja fissure swarm, and what will be known as the all-around fissure eruption site. So, 5 years ago, in August, the IMO, the Icelandic Meteorological Office, noticed increased seismicity at Bardarbunga beyond background levels. A few days later, lateral propagation of seismicity began at the southeast edge of the caldera. Eventually, the seismicity underwent a change in direction, went towards the northeast. Some 40 kilometers away from here, eventually a fissure opened and lava outpouring began. This volcanic activity went on for half a year until it eventually ceased in February 2015. When looking at the volume of erupted material, this is the most voluminous fissure eruption in Iceland since the Laki fires in 1783. At the same time, we had caldera subsidence in the Bardarbunga Central Volcano. So here's a picture of the caldera. And here's the data that was produced. There were GPS measurements done, and it averaged at 1 meter per day in the end of subsidence. Given that just 4 years earlier we had the big Eyjafjallajökull eruption in 2010 that disrupted air traffic in most of Europe, it is not surprising that the media was nervously looking onto Iceland in 2014, because fears were high that this could turn into another Eyjafjallajökull and that air traffic will be disrupted again. And this is actually a news article from last week, because we're 5 years in, so it was just an anniversary. At the same time, one of the questions that scientists were asking was actually, where did the magma originate from? We have seismicity at Bardarbunga's central volcano, yet we have lava outpouring some 40 kilometers away in a different fissure zone. So what we did, we first looked at some major and trace elements. We have several plots here, and what we plotted is, of course, the eruption itself, which is the 2014 eruption, yellow. Then we had some older eruption from an older eruption at Tonneram, and from Tullerraum, which is the same volcanic system. We also looked at data from the literature from Askja volcanic system, and we compared them. And what you can see in all these diagrams is that two groups emerge. One is the Askja group, and one is the Bardarbunga Vedivertan system. So already here you can see that the lavas produced seem to be of different composition. Looking further at the mineralogy, we have in our samples we had fibrils of kleiner Parksing. What you can see is that we usually find multiple zones and an outer rim, which is usually embayed and sometimes overgrown. You can find some small increases on the ground mass in the rim, for example, plagioclase, or even olivine, smaller olivine. When we look at plagioclase, we see that we have 3 crystals over here, and they're redrawn down here, so you can see the features a bit better. We can see that most plagioclase show sieve textures, also show overgrown but resolved rims. And all of the crystal faces that we can find, all the mineral faces, they also appear as glomerocrysts in our samples. In addition, what we found were gabbro fragments, up to a centimeter in size approximately, usually olivine and plagioclase, which you can see here and here. We wanted to assess the plumbing system, so what was going on under the volcano. One of the methods that can be used to do so is mineral melt thermobarometry. This method estimates pressure and temperature by applying certain calibrated equations to a set of geochemical data of minerals and an associated melt. So these equations are usually based on the relationship of some thermodynamic property of the mineral to the physical property present during their crystallization. There are many different approaches that exist. Some make use of exchange reactions between minerals and the coexisting melt. Some look at the cation content in minerals and the coexisting melt, while others look at pressure-sensitive variations in the crystal lattice structure or at phase relation of a set of minerals. So let's look at the minerals in the Holloran lava again and use some of these models. In this case, we used the model by Butirka from 2008, which is based on J-Hedenberger diopside exchange. And over here is a frequency plot. This is how we usually display the results of our thermobarometry. So over here you have depth in kilometers, and up here you have a frequency, so number of crystals that show a certain depth. If we look at our kleiner Parksing over here, or the red bars, we can see that our results show that kleiner Parksing crystallized at 26 to 882 megapascal, which translates to, on average, to 471. And if we look at the depth, that translates to 70 kilometers. So we have a peak around here. Plagioclase, on the other hand, seems to crystallize shallower. So we have 103 to 165 megapascal with an average of 114, which translates to around 5 kilometers, as you can see by this nice peak over here. So our results actually are in agreement with other geophysical studies, but I'll come back to this in a second, so keep this in mind. Another way that we can assess crystals is oxygen isotope geochemistry. Oxygen isotopes actually provide a very powerful tool to fingerprint rocks and minerals, and we can investigate the role of different inputs during magmagenesis. Technical advances in the last 50 years enabled higher resolution. We went from whole rock, from the conventional line, to crystal analyses on the laser fluorination line. So let's fingerprint our Geiger fragments and see what happens. Down here is an oxygen plot. You can see the normal range for mid-ocean rich basalt, as well as the line for as far as fractional crystallization would take us if it would have happened. So again, our polyron lavas are plotted in yellow, our Geiger fragments in green, and I have some literature data on mafic eruptives from Iceland and on some hydrothermally altered crust. What we can see is that both our Geiger fragments and our lava plots lower than warp. Our Geiger fragments are even a bit lower than our lava. So the delta AT0 range for the lavas is around 4.4 to 5.4 per mil, with an average around 5, and the fragments are 4 to 5 per mil, with an average around 4.5. So the question is, they might have incorporated some altered crust during crystallization. Putting all this together, we came up with the following model. We envisage some vertical ascent first, with storage around 15 kilometer depth. That's what our climate biopsy said. Before further ascent, right under the Badabunga to around 5 kilometers. That's what our plagioclase said. Before a dike was injected, and we eventually had our eruption. I mentioned that geophysical data says similar things. So we know that GPS displacement modeling points to a source at around 16.8 kilometer depth, which overlaps with our climate pyrocene crystallization depth. At the same time, earthquake hypocenters at smaller than 5 kilometer depths were noted, which overlaps with our shallow source. So what we can see is that lateral transport might have been underappreciated in this whole system, because we had activity at Badabunga and an eruption eventually next to Askja in the Askja fissure zone. Okay, let's move a little bit further south, where it's a bit warmer, to Gran Canaria in the Canary Islands. Here's a map of Gran Canaria, and our study area will be approximately here. And you might have seen it in the news. This area over here is literally on fire at the moment. Big forest fires are raging on the island at the moment. But let's go back and see what we actually did. So Gran Canaria is the third largest island of the Canaries and located approximately in the middle. It went through three major geological phases. One is the Miocene shield phase, then the Pliocene phase, and eventually followed by the Quaternary Holocene. A prominent feature of the island is the Miocene Tejeda collapse caldera in the western central of the island. Inside this caldera, we can find cone sheets and abyssal cyanides. I'll keep relating to them as cyanides for simplicity. However, these exposed cyanides that we can find in the middle of the island, they've already shown to be hydrothermally overprinted. If we want to look at plumbing systems and apply thermobarometry to them, we usually need fresh crystals to get good estimates. So we were looking for fresh cyanide boulders, which can be found in conglomerates. The fieldwork was very hard, and we had to plan it really well to get these boulders. Luckily, I recorded all of this, and I brought you a little insight in our sampling mission. So here you go. So eventually we managed to find all boulders. I passed some around, you can look at them. We went back to Uppsala and we looked at them a bit closer. So what do we find? We find alkali feldspar, which are usually twinned and show some overgrowth of amphiboles and oxides. The amphiboles show dissolution features and overgrowth by oxides. Our climate pyroxene also showed dissolution features and overgrowth by oxides here and there. All of the mineral phases can again be found as glomerocrysts. When we looked at the geochemistry of the cyanides, we prepared 3 diagrams. Over here is a normal task. This is a platonic task, and then see that Canary Island rocks usually span the full compositional spectrum, that is plutonic rocks and volcanic rocks. So we have rocks from Gran Canaria and rocks from Tenerife as a comparison. If we now plot the cyanides and cone sheets on the plutonic task, we can see that they fall into the nepheline cyanide field. When looking on the zirconium versus niobium plot, two fields were previously identified. One is the Mogan trend, and one is the Fataga trend. We see that our cyanides and the oldest cyanides actually plot along the Fataga trend. Other plutonic singulars, which were found in ignimbrite A and X, plot the Mogan trend. Looking at some oxygen, we have an oxygen for the silica plot down here. And you can see over here is the field for fresh cyanides. And you see that our cyanides, which have an average delta 18O value of 7.1 per mil, plot right into the field of fresh cyanides. In comparison, altered cyanides and some of the cone sheets plot the whole spectrum from low T hydrothermal alteration to high T hydrothermal alteration. So now convinced that our cyanides are somewhat fresh, we use them for thermobarometry calculations. In this case, we use the model of Masota et al., which is calibrated for evolved alkali systems. Again, our Klein-Barksine record pressures between 133 and 351 megapascal, which translates to depths of 5 to 13 kilometers, with a nice peak around 7 to 8 kilometers. Once again, we looked what the literature says, and we see that some older barometry had results of 4 to 14 kilometer depth, looking at oxides/silicates. Modeling by cone sheet intersection points to a minimum depth of 2 kilometers for the magma chamber below the old Miocene volcanism or the Fataga volcano. Okay, we can move on. We move to Cameroon, and we're going to be looking at Mount Cameroon. Mount Cameroon is one of the biggest volcanoes in Africa, with over 4,000 meters in elevation. It is part of the Cameroon volcanic line, which spans approximately 1,600 kilometers of oceanic to continental volcanoes. Mount Cameroon had 8 major volcanoes in the last century alone, of which we're going to be looking at the 99 and 2000. Additionally, it showed short-lived volcanic explosions or outbursts in 89 and 2012. So in between major eruptions or after major eruptions. Despite that this volcano seems to be quite active, the flanks are densely populated for over 500,000 of people. But little to no warning system actually exists. When looking at the geochemistry of the 1999 and 2000 eruptions, we chose the niobium for this potassium plot, and there was some previous work done on the 82 and 59 lavas. Our lavas can be seen here, which is the 99 and the 2000 in red and blue, and these are literature values on the same two eruptions. So we can right away see that the 99 and 2000 lavas display higher niobium and potassium values than the 82/59 lavas. They fall into a projected mixing line between the 82 to the 99/2000 lavas, which is quite similar to the previously identified 59 to 82 mixing line. When looking at the crystals that we find in the lavas, we again applied plagioclase and Klein-Barksine thermobarometry. So if we start this time with plagioclase shows a major level of crystallization between 26 and 39 kilometer depth, which you can see here by this purple line. The dominant zone for our Klein-Barksine is a bit shallower, around Moho level, between 20 and 28 kilometers depth. The 2000 eruption is quite similar. Plagioclase is a little bit more shallow in this case. Again, when we look at geophysical methods, we see that there were earthquake hypocenters at 30 to 55 kilometer depth, which overlap with our deep storage zone. Other seismic and petrochemical studies suggested a feeder reservoir at around 20 kilometer depth, which again overlaps with Moho level. However, what we see is that the 99 eruption, Klein-Barksine in the 99 eruption, So these might be the reason for the seismic unrest and the short explosive outbursts in between eruptions. So when we have magmas migrating. And they might be an indication for future eruptions. Reaching our final destination, we go to Bali, and we're looking at Agung and Batur volcano. So those two are two active quaternary volcanoes on the island of Bali. You can see Agung here in the east, and Batur, its twin sister, a bit to the northwest. So Agung is over 3,000 kilometers high. You can see it from here, looking towards the south. And its name translates to paramount, because it is of religious importance to the Balinese people. Its last major eruption was in 1963. Batur, its twin sister, is located in a double collapse structure and had over 20 eruptions in the last 2 centuries. We're going to be looking at the 63, the one that happened at the same time as Agung erupted, and the 74 eruption. Why was the 63 eruption so important? Well, it was the first eruption after 120 years of dormancy. It caused approximately 2,000 fatalities, and therefore it was the most devastating event in Indonesia since Krakatau in 1883. Additionally, it released huge amounts of SO2 and of chlorine, which eventually caused a drop in average northern hemisphere temperatures of 0.3 degrees, which makes it the 4th largest atmospheric perturbation in the 20th century. Taking all of this together, it is clear that this is one of the most significant volcanic events of the 20th century. Looking at the petrography of Agung, we have phenocrysts of plagioclase, orthopyroxene, clinopyroxene, and titanomagnetite. Our plagioclase is zoned and shows slight resorption features, while our clinopyroxene shows inclusions of titanomagnetite or exsolution of titanomagnetite. Titanomagnetite can also be found as phenocryst, but usually associated with clinopyroxene and low-barrel crystal. Looking at Batur, we have plagioclase, clinopyroxene, olivine, and titanomagnetite. So no orthopyroxene, but olivine in this case. Again, our plagioclase is quite sieve, so we have sieve textures, while the clinopyroxene shows resolved rims and titanomagnetite inclusions. Olivine shows fine rims with titanomagnetite inclusions. Once again, we can find all mineral phases in crystal clots. Looking at the crystals, first for thermobarometry, we see that clinopyroxene crystallizes around 20 kilometers depth around the mohole. Plagioclase shows shallow crystallization around 5 kilometers depth. When we look at oxygen isotopes of the crystals, we see that plagioclase shows values of 6.2, which translates to a melt value of 6.0 per mil, while clinopyroxene shows 5.5 per mil, which translates to a melt value of 5.8. We also did some helium on the clinopyroxene, which show a value of 8.62 Ra. Just as a reminder, a usual mantle value for helium is 8 plus minus 1 Ra. So both our oxygen and helium isotopes corroborate the mantle-like origin of our crystals. We also found some INSAR data in the literature, which points to a magma chamber at around 2 to 4 kilometer depth, which overlaps with our shallow crystallization depth. When looking at Batur, the 63 eruption on the left and the 74 eruption on the right, we see a similar picture. Clinopyroxene seems to crystallize right above mohole for both eruptions, while plagioclase shows shallow crystallization around 3 to 4 kilometer depth. We have oxygen values for olivine, which is 4.7 for the crystals, which translates to 5.1 per mil for the melt, while clinopyroxene shows 5.3 per mil for the crystals, which translates to 5.6 per mil for the melt. And finally, plagioclase shows crystal values of 5.8 per mil, which translates to melt value of 5.6. Once again, our oxygen values corroborate our mantle-like signature of the crystals. If we look at earthquake clusters, there are reports of clusters at around 1.5 to 5 kilometer depth, which overlaps with our plagioclase crystallization depth. Putting this all together, getting a model which is similar to this. So we have a source-dominated system for both volcanoes, as shown by our oxygen isotope geochemistry. And it seems that lithological changes control the stagnation of the magma. So we have two very similar, but if you remember that we had a different mineralogy that Agung showed orthoparoxene, while Batur showed olivine, we have still separate plumbing systems, at least for the 63 and the 74 eruption. If we look onto magma storage along the Sunda arc, we have Krakatau, Gede, Merapi, Helut, and our two volcanoes. We see that a quite similar picture appears for all of the volcanoes. They usually show some shallow storage. This was all attained by thermobarometry. And we can find some storage around the Moho. Once again, Agung was in the news last year. It was showing renewed activity. And this was interesting because we have a map of Bali here, and as you remember, Batur lies here and Agung here. It seems that this time seismicity seems to originate below Batur and then moving laterally towards Agung, similar to what happened at Bardabunga, where seismicity originated beneath Batur and went towards Askja. So maybe there's a connection after all. So more work needs to be done. Also, maybe not surprisingly, we had a lot of attention due to Agung being in the media, and we even got a little award. Putting this all together, we see that for all our systems, we usually see a multi-tiered magma system in all our regimes. Lithologic boundaries seem to play an important role during emplacement of all our magma levels or magma storage levels. So we see that improved understanding of these shallow magma bodies especially may provide vital information in order to explain and assess sudden and explosive